So check out the next question. Assume op amp ideal and R equal to root of L by C. Calculate the phase angle between output V0 and input Vi at omega equal to 1 by root LC E given. So this is the op amp circuit. So input containing the impedance elements R and C and feedback circuit containing L and R you can call. So asking that what is the phase angle between V0 and Vi at omega equal to 1 by root LC. See, for now, here the signal is applied to the inverting terminal and non-inverting is at the ground. It looks like a inverting circuit. So it is a inverting circuit you can call. Okay. So now this is the input impedance. Now I can call as a sum Zi. So this is the impedance in the feedback path that I can call as a sum ZF. So the impedance in the feedback path that I can call as a ZF. Now I can calculate Zi and ZF there. See, for now, Zi is the input impedance considered by R and C. So both are in series. Now I can write this one R. Capacitive impedance is nothing but 1 by j omega c in phasor form. 1 by j omega c. Right. Now I can substitute the value of R. R is given as a root of L by C. Right. Plus 1 by j C divided by omega equal to 1 by root LC given. So that I written like this. 1 by root LC. So now I rewrite this root of L by C. 1 by j become minus j. C by root LC becomes root of C by L. So rewriting as root L by C again. So in both of that, now I can take root L by C common. That become as 1 minus J1. So this would be the input impedance you can call. Now I can able to check out like that feedback impedance now. Now I can able to go for the feedback impedance ZF. Now I can able to discuss. And ZF is the feedback impedance considered by what means. So ZF is the feedback impedance considered by L and R you can call. So now that is also the series combination of L and R that equal to R plus j omega L you can call. R plus j omega L you say. Now I can able to say that ZF equal to R means again I rewrite as a root of L by C. J L omega equal to 1 by root LC you can call. Right. So ZF equal to root of L by R equal to root of L by C. Omega is substitute as a 1 by root LC that become as a JL by root LC you can call. Now I can minimize. By that what you can get means. So ZF equal to. So if I minimize that, you may get this one as root L by C plus J of root L by C you may get. So take root L by C common from both. You may get as 1 plus J1. Right. Check out this. So root L by C. JL by root L. When root LC becomes root of L by C there. Taking root L by C common, that become as a 1 plus J1. So Zeta is this value. Root L by C into 1 minus J1. ZF equal to this value you can call. So it is inverting circuit. The gain of the inverting circuit you know. For inverting circuit, the gain A dash equal to some V0 by Vi. So in terms of the impedance, you written this minus ZF by Zi. So if I substitute both of that, so in ZF and Zi, root L by C is common, right? So here root L by C is there root L by C is common. Then what the thing you may get means minus of 1 plus J1 divided by Zi value root L by C cancelled, remaining become 1 minus J1. So 1 plus J1 divided by 1 minus J1 you may get. So now I can able to divide these complex values means each to be written in terms of the polar form. Then V0 by Vi equal to minus, in terms of polar form, it is root 2 angle of 45 degrees. 1 plus j1 in polar form is root 2 angle of 45 degrees, you can call. Like that, 1 minus j1 I also you can write, that is root 2 angle of minus 45. So root 2 cancelled out, that is minus 1 angle of 90 you can call. So minus 1 indicate 180 degree phase shift because it is an inverting circuit there. This minus 1 indicate 180 degree, that is the phase angle for the inverting circuit, and LRCR components of this circuit gives 90 degrees phase shift, so that the total phase angle between input and output is 270 degrees, where 180 is considered by the inverting circuit and 90 degrees considered by what means LR and CR circuit, CR components of the circuit. The total phase shift between V0 and VA is 270 degrees. Okay, check out the next case. So this is the next question you see. Assume op-amp ideal, calculate current I0. Assume op-amp ideal, calculate current I0 you can call. So this is the op-amp circuit is there. To the inverting terminal, the voltage applied is 3 volt, and at the output node a BJT is connected. So this is a BJT common emitter circuit it is. So this is emitter, this will be the base, this will be the collector, and the collector supply voltage is 8 volt there, and he given a feedback from transistor emitter to the inverting node you can call, and this emitter load is nothing but 20 ohms. He asking that this current I0. Here you observe now, this current I0 should be same as what means base current IB. It should be same as base current. That is going to be calculated, that is going to be asking. Let us see this one now. Using virtual ground, so what are the voltage at this non-inverting terminal to be repeated there? So the voltage at this one to be 3 volt you can call. Using virtual ground, the voltage at this emitter node should be 3 volt using virtual ground phenomena, and here it is emitter terminal. So in this one, the current that is passing is emitter current IE. Confirm? So using virtual ground, I written that the voltage is 3 volt. What is the voltage of this 3 volt to be repeated again at this corresponding terminal? So that emitter node voltage is not but 3 volt you can call, right? Using virtual ground, right? Emitter node voltage is 3 volt I say. Emitter node voltage is 3 volt. Then I can calculate emitter current IE through that emitter load. So that become 3 by 20 ampere. 3 by 20 ampere. That become as 0.15 ampere. So beta given, beta of a transistor given 80 now. Now you asking I0. I0 should be same as base current, you know, right? So that to be written as IE by 1 plus beta. Okay, now written that a base current IB equal to what means IE by 1 plus beta. How to write that one means, see this one now, you know that IE equal to IB plus IC, you know, right? Again, you know that IC equal to beta IB for common emitter, IB plus beta IB you can call. So taking IB common here, you may get IE equal to what means 1 plus beta times IB you can call. So if I take IB common from this, you may write that IE equal to, IB equal to IE by 1 plus beta. So by that I written there, IB same as I0, IE equal to 0.15, beta is 80, that become 81 ampere. So if I minimize this current, corresponding current may come around 1.8 milliampere. So the value of I0 is 1.8 milliampere. Okay, you know this. Check out the next question. So check out the next question now. Assume op-amp ideal, calculate the voltage at node A. So you're asking the voltage at this node A for this op-amp circuit. He said that op-amp should be ideal. Okay. Suppose Here, if I go for virtual ground, it is already 0. Then node A to be at 0 volt, you can call. The corresponding node A is also at 0 volt. Is it right or not? Now I can able to examine. At this inverting node, the voltage applied is 1 volt, input resistance is 1K, and the feedback resistance is what means 31K, you can call. Now I can able to examine, is it right or not? So according to the ideal condition, so as this one is nothing but V2, you can call. This is V1, suppose. So as V2 equal to 0, then the voltage at node A to be 0, right? So first that I consider as V2 equal to 0 volt. Then voltage at node A, that is V1 equal to 0 volt using virtual ground, I said. Is it right or not? I can able to check out. So now I can indicate the current flows here. Okay. So I apply KCL at node A now. I apply KCL at node A. KCL at node A now I call. Okay. So 1 minus. So we node A voltage V1, that is nothing but you can call as a 0 there. So first I write this one now. 1 minus V1 by 1K equal to, so V1 minus V0 by 31K you can call. K cancelled out, and you say that V1 0, then this becomes 1 minus 0 equal to, so 0 minus V0 by 31. That implies V0 equal to minus 31 volt. So taking the voltage at node A as a 0 using virtual ground, V0 becomes how much, means minus 31 volt there. But you observe now the saturation voltages is plus 15 and minus 15. So which is not possible, right? Which is not possible as plus or minus saturation value is plus or minus 15 volt only. So the corresponding saturation voltage just plus or minus 15 volt only. So that thing is not possible there. So what are the thing you can able to examine means, so virtually I want that output is minus 31 volt, but that you say that not possible. So that the output should be clamped at what means the negative saturation value, that is nothing but minus 15 volt now. Therefore, output V0 clamped at output V0, what you can call clamped at output V0 clamped at minus 15 volt only, because output is negative. So negative saturation value, that is minus 15 volt. That implies V0 equal to minus 15 volt. Remember now, if the voltage node A is 0, at that time output must be minus 30 volt, minus 31 volt you can call. But output is not minus 31 volt, it is just minus 15 volt to come. Now you can call, so that the voltage at node A not become 0. So what will I do means, again I consider that what is the voltage at node A, taking V0 equal to what means minus 15 volt now. So this is the equation you can call, that I can consider some equation 1. So there I can able to substitute V0 equal to what means minus 15 volt to get the value of the voltage at node A, right? Check out that. From equation 1, right, on substituting V0 equal to minus 15 volt. Okay. So this is the equation 1. On that I substitute now 1 minus V1 equal to, so this is the equation 1, 1 minus V1 equal to V1 minus V0 by 31. V1 minus V0 by 31 you can call. right? Now I substitute that value there. 1 minus V1 equal to, so this becomes V0 is minus 15 is there. V1 minus of minus 15 divided by 31 I say. Okay, take this one this side. So 31 minus 31 V1 equal to V1 plus 15, right? So take this one this side, that becomes 32. So take this one this side, this becomes 16. 16 equal to 32 V1 you can get. Implies V1 equal to 16 by 32, that is 0.5 volt, right? Therefore, the voltage at node A, is not 0 according to virtual ground you call. So that is how much means 0.5 volt, because E specified that saturation voltages, that is just plus or minus 15 volt. If I apply that virtual ground there, you mustn't should get that output equal to minus 31 volt, which is not allowed there. So because of the saturation value just plus or minus 15 volt. So based on that output just clamped at minus 15 volt you can call. With that one, the voltage at node A now not becomes 0. So that value you calculate as 0.5 volt. Okay, let's know this. So next question you check out. So assume op-amp ideal, calculate the input impedance Vi by Ii. So for this circuit, you're asking that input impedance Vi by Ii you can call, right? See, so now I can able to examine, this is a closed loop circuit you can call. Here the signal voltage is Vi, no impedance element here. So now using, now here the node voltage is Vi there. So using virtual ground, here also you may say that the voltage should be Vi. So what are the voltage here? Vi you can call. The same voltage is also be considered the other node. Now indicate the current flows in each branch to get that concerned impedance. So now I can able to apply. This is some node 1 I can call. This is some node 2. So here Vi is there. So using virtual ground, other node also the same voltage Vi I can call. Now I assume that what is the voltage Vi here? The same voltage it is acting. Now I can able to apply the KCL at the concerned nodes to say 1 and 2 to get the input impedance Vi by Ii, right? Now check out now. KCL at node 1 I can go. KCL at node 1 in our circuit now indicated. Okay. So you observe now here incoming is nothing but current Ii. Here it is outgoing is nothing but what means Vi minus V0 by Z you can call. So Ia is the incoming current there equal to Vi minus V0 by Z. Vi minus V0 by Z. Now I can keep as a sum 1. Now I can able to apply KCL at another node 2. KCL at one more node, say 2 now I can call. So if I apply the KCL at node 2, none of them is incoming, both are outgoing you can call. So incoming is 0, outgoing I can call, node voltage is Vi, here it is Vi by R2, Vi minus 0 by R2 means Vi by R2 it is, plus this is Vi minus V0 by R1, Vi minus V0 by R1 you can call. Got it now? Now I can able to calculate V0 and then I substitute to get the impedance now. So take out this V0 by R1 this side. So minus V0 by R1, take this side become plus and take Vi common. It become LCM as R1 R2. This is R1 plus R2. Got it? So minus V0 by R1 I take this side, that become as a plus V0 by R1. So if I take LCM for that, Vi, right, R1 R2 if I take, that is nothing but R1 plus R2 by R1 R2 you can call. R1 get cancelled there. So now what will I do means I substitute the value of V0, that is Vi into what you can call 1 plus R1 by R2 you can call. So I substitute this one in the equation 1. So I substitute that one in the equation 1 to get the corresponding input impedance now. So this one now. So Ia equal to, from equation 1 I go. So from equation 1 I go. So from equation 1 I substitute this one now. Ia equal to Vi minus, so V naught, what is V naught there? Vi into 1 plus R1 by R2 by Z. Okay, so Vi into 1 plus R1 R2 by Z you can call. Now Vi get cancelled, then whatever that thing you may get there, so Vi may get cancelled, then you may get like this. Ia equal to, so the corresponding input current Ia equal to, remaining is what means minus Vi R1 R2 by minus Vi R1 R2 by Z it comes, minus Vi into R1 R2 by Z it comes. So from that you ask that input impedance Vi by Ia becomes minus ZR2 by R1. So this will be the input impedance Vi by Ia from that concerned circuit. So in this circuit you are asking that input impedance Vi by Ia you can call. So in that circuit you are asking the input impedance Vi by Ia is so Vi by Ia is asking. So now, right now I consider that using virtual ground, what are the voltage Vi there? It is also acting at the other node I can call. Now I assume that nodes 1 and 2, I apply KCL at the concerned nodes to get the corresponding input impedance. So for node 1 I apply that Ia I got. So from node 2 I apply the KCL. So based on that I can get that what is the value of V naught means Vi into 1 plus R1 by R2 I told. I substituted this one in the equation 1. Thereby I calculated that Vi by Ia equal to minus ZR2 by R1. So this will be the input impedance of that circuit. Okay. Check out the next question. Assume op-amp ideal. Calculate the current Ix. So this is the op-amp circuit. In this circuit, he asked for the current Ix here. Okay. So now, using virtual ground, this is 0 volt means here it's also be 0 volt you can call. So here 0 volt is there means here also what's means 0 volt you can call. And so now, using virtual ground, what are the voltage at one node that should be repeated there? This one is also at 0 volt. Now I can indicate the current flows in each branch. This is 1K, supply is 2 volt. This is one more 1K. This is 2K, 2K. This current is asking Ix. Now I indicate the current flows in each branch. Now I can call this as a node 1. I can call this output node as a node 2. Okay. So now I can able to go for KCL at node 1. So using virtual ground, what are the voltage 0? The other node is also same one, 0 I can call. I can able to check out KCL at node 1 first. KCL at node 1 I go. If I apply KCL at node 1, what is this one means? 2 minus 0 by 1K equal to 0 minus V naught by 1K it comes. Okay. That becomes V naught equal to minus 2 volt. Take as a 1. V naught equal to minus 2 volt you can call. Again I apply KCL at node 2 to get the required current Ix. KCL at node 2 now I go. So this is incoming current, this is also incoming current, and this will be the outgoing current there. That is 0 minus V naught by 1K. This is one of the incoming current plus, in this branch the current coming is Ix, that I need now, equal to, here the current is nothing but V0 by 2K, you can call, right? Now I need Ix there. So taking this side, that becomes plus V0 into, so this is 1 by 1K plus 1 by 2K, you can call. So V0 into, so 1.5, take K to the numerator, become what means milliamps. V0 into 1.5 milliampere, you can call. What is that V0 there? Already know V0 equal to minus 2 volt from equation 1, minus 2 into 1.5 milliampere. So the concerned current Ix is minus 3 milliampere. Got it now? So using virtual ground, what is the voltage here? 0. That should be the same, or the other node I can call. I consider this is node 1 and the output as a node 2. Just I apply the KCL at node 1 and node 2 to get the concerned current Ix value. So that come to be how much means minus 3 milliampere. Okay. Check out the next one. So this one now, assume op amp and diodes are ideal. Calculate the output V0, you can call. So in this circuit, both diodes and op amp are ideally called. Asking that what is the output V0, you can call, right? So this one now. So this is the op amp circuit. There I can consider this op amp output is some Vx. Okay, this is final V0. This is the Vx output I can call. Here the signal voltage is applied to the inverting node, you can call. So it is an inverting circuit. It is inverting circuit. Okay. So in the case of inverting circuit, the output and input are in opposite phase, you can call. Then concerned output is Vx and input is Vi, you know, are in opposite phase, I say. So both are in what, sir, means opposite phase. Suppose if Vi is a positive, that is greater than 0, then Vx is positive. If Vi is less than 0, that is negative, Vx is what means positive, we can call. Check out now two cases. Okay, case one, first one I can go. For Vi greater than 0 volt, that is Vi equal to positive, then Vx equal to negative, right? Vx equal to what? Negative. And again you see this one now, this is already ground. Using virtual ground, this is 0 volt, you can call. So for a diode D1, you observe now, cathode voltage is Vx, that is negative, anode voltage 0. So anode is positive than cathode there, anode is positive than cathode, you can call, so that the diode D1 is on, right? Therefore, by that D1 on. Confirm my option, how it is. So cathode voltage is Vx, that is negative there, anode is at 0 volt, that is nothing but positive than compared to cathode potential, so that the diode D1 should be on. Whatever the diode D2, we can come back. So for a diode D2, this corresponding Vx is negative, so anode is at negative potential, means D2 become off. D1 on and D2 become what means off, you can call. D1 is on and D2 become what means off. Okay. So D1 on and D2 become off. Right. So in this circuit, now I can able to maintain this corresponding D2 as a open circuit. In this circuit, I can keep this D2 should be as a open now. See, so now what happened there? If I keep this D2 as an open part like this, just I do it now. So this D2 look like as open there. Then what you see, sir, means this output node is open. This output node is open such that output is not possible to calculate here. So D2 should be open path. So keeping that diode D2 as an open, this output is not possible to calculate, right? Then V0 is unable to calculate. So in first case for VA greater than 0, this is open one, so that output V0 is unable to calculate now. Now I can able to go for case 2 now. So I can keep to connect the same diode as it is again here. What are the diode D2 there? That I connect now as it is. Okay. Now I can go for the next case, that is for Vi less than 0 volt, that is Vi equal to negative, then Vx equal to positive we can call. Vi equal to negative means concerned Vx would be opposite phase of positive. So anode is at 0, cathode at positive potential we can call, thereby the diode D1 become off. In this case, D1 become off. Diode D1 become off user. And whatever that diode D2 means, so Vx is positive means, so that diode D2 become on. D2 become on. Right? In the case 2, D1 off and D2 on. Now I can able to do that now. Now I can able to check out that condition now. So D2 on, D1 off, sorry, D2 on, D1 is off. Now I can able to check out this. This is off. This is on. I can make it as a close now. Like this. So now I can able to connect that one. This is the circuit now. So in this place, what are the D1 should be off condition, D2 should be on condition now. So this is the equivalent model for the second case I say. So in this place, what are the two D1? That should be off like this. D1 should be open condition. D2 should be on condition you can call. So it is open means no use there. It look like inverting circuit you can call. Then whatever the output V0 means. So from the inverting circuit, V0 equal to already know minus R2 by R1 into Vi. Right? Circuit look like a inverting model. So V0 output V0 equal to how much means, you know that minus Rf by R1 into Vi. Rf place is R2, R1 place as it is R1, input is Vi there. So output V0 equal to minus R2 by R1 into Vi. Confirm this? So circuit is of inverting model. So this diode D1 is open, no use. So Rf place is R2, R1 place is another but R1 as it is. Already you know that output of the inverting amplifier is V0 equal to minus Rf by R1 into Vi. So from that I write that value. So Rf place is nothing but R2 there, R1 as it is. Like this you can get. So this is the output of this corresponding circuit. Okay.